Hi and welcome to the second part of my Part in a Briefcase video, and this video I'm just going to be going over how I designed the circuit to take the load for Arduino, and this is basically how I'm driving the LEDs. Now these little things are brilliant. They're called an RFP12N10L, and they're capable of taking up to 10 amps of current at up to 100 volts. I know it says 12 amps there, but actually I know that 10 amps is probably the limit if you don't want to blow these things up. Now I'm not going to be switching anywhere near that. These LED modules that I've got, they take around about 0.9 of an amp at the most. They'd take a little bit more if I was running them on 12 volts, but with my usual caution I've actually dialed the power supply voltage down to 11.5, and the reason for that is I don't like running anything anywhere near its maximum capabilities. That includes the LEDs and everything else, and automotive stuff is generally classed to run as low as 10.5 volts, so 11.5 is fine. It gives everything, like the radio, plenty of headroom, and it makes the LEDs last a bit longer. They'll last a long time anyway, but this is just me being cautious because I'm me. Now these little beasts are amazing. They're really good, and I wish they had these back in the day when I was designing a lot of stuff, because this gate pin here, this simplified diagram, there's a lot of circuitry inside here, because this gate pin here runs at logic levels. Normally with power FETs you have to get the gate pin somewhere near the input voltage, so it'd have to be somewhere near 12 volts to turn it on fully. So the Arduino wouldn't be able to manage that because it'll only shove out about 5. However, with this being designed so that it's switch on voltage between the source here and the gate is only 2 volts or so, the Arduino can drive this with no problems, and in fact it only takes around about 1/4 milliamp to do so. And they come in this nice little package here which you can put on a heatsink, but because I'm running them at only about 1/10 of their rated amperage, I'm not worrying about heat sinks. Now if I was running it at say 25 or 30% of its max, I would worry about heat sinks, but experience tells me this is no problem at all in this design. If you're using a big beefy motor or something like that rather than an LED to turn on and off, please put a heat sink on these devices. So that's what I'm using. So how about the circuitry? Well, the circuitry is very easy, and here it is. I've pinched this circuit diagram. It's not mine, but hey, and it shows a motor. Whoopie-doo, we're not using a motor. This is going to be an LED, but it still applies that you have the positive end of the LED connected to plus 12 volts, the negative end of the LED connected to the drain on this device, and the ground connected to the source. And the Arduino output pin can just go straight in. So you don't get much of a simpler circuit than that. So that's the drive circuit out of the way, and I'm using this to drive 4 things. The 3 LEDs, the RGB LEDs, and a strip light which will simply flash on and off with the volume. So what about software for the Arduino? Well, I've written one, and here it is, and I'll go through it bit by bit. It's very easy to follow. Now to start with, you declare all your output pins, and I'm connecting the main flashing on and off LED to 13, and that also, by some strange coincidence, is the internal LED on the Arduino, so you can see it flash on and off, so you know the Arduino is working. The red LED module I'm connecting to digital output 2, the green 3, the blue 4, and I'm declaring some other integers here sequence, which is a thing that I'm going to determine which LEDs flash on and off out of the RGB, and the timer for the off. And I didn't originally have this, but it's much better with it, because basically otherwise the LEDs just flicker on and off so fast you can't even see the off. So you need them on for a certain minimum time. The next one I'm declaring is a threshold value. Now this is only a start point, because this software will actually modify that depending on what the input signal level is, which is cool. Volume, which is where we stick the actual reading from the analog to digital conversion. Trigger, which is a counter that triggers it counts how many times the LEDs are turned on. Run, which is a run count and how many times around the loop we've gone. The on time. On time 2 I don't think I used, I can probably delete that. And off time, and the state, which tells you what state it's in. Surprise, surprise, whether it's actually currently on or currently off. Now the setup routine is always the next thing executed, and the important thing is to declare all our pins as outputs and to write them low for safety's sake, because you don't want it turning on, getting hung up, all your LEDs are turned on and they're just sat there getting hotter and hotter. Now you've got the main loop, and this is what the program executes all the time. So the first thing it does is reads in from the analog read pin. Now connected to that I've got a little third-party module, which is basically a microphone and an amplifier that you can buy online. I think they're about £4 or so. Very easy. Then I've got a delay for 1 millisecond, just to make sure that everything settles down before the next time this gets read, because it'll whip through this loop very, very quickly. Now if the state is greater than 1, then the on time, actually yeah I did use on time too, then the on time gets incremented. So in other words, if it's on, you're counting the fact that it's been on for a while. If the volume is greater than the threshold, then I increase the trigger value, which says I've turned the LEDs on. And then if the off time is greater than 50, and these are things that I set just by playing around, then it basically writes the LED high, so it'll turn it on if the off time is greater than 50. So that means that basically it's going to stay off for a little while. And if the on time is greater than 100, less than 100, then it'll write the LED high, so it turns on the main gosh I've got some noise LED. Otherwise, if none of those things, then it requests that the LEDs be turned off. Now why requests it? Well, because I want the LEDs to turn on for a certain minimum time. Otherwise, as I say, you just get a really fast flicker that you can't even see, and that's not what we want. We tell the system the LEDs are on, and we increment the on time. Now if it's not greater than the threshold, then if the on time is greater than 15, we reset everything, we go through the sequence, which I'll show you in a minute, which actually lights up the RGB LEDs. Now a lot of people, when they're doing sound to light, they will go and they will use one of the Arduino libraries that actually allows you to do frequency analysis. Now you don't actually need to do this, and the human mind is very good at constructing patterns from flashes of LEDs amongst other things, and this will look exactly like you've got all that expensive runtime overhead of analysing the frequency, when in fact you don't. And this is a very good thing, because the Arduino I'm using is a very tiny one called the Arduino Nano, which I'll show you in the next video, simply because it's got to fit in a briefcase. It's very small, it's got limited capabilities, so I didn't want to go through all the expense of analysing the frequency. Not that it's expensive for me in terms of software, because it's just a library that you call. So then we request off, and turn off time as being off time +1. Run is run +1, which tells you how many times it's been through the loop. If the run is greater than 1200, then we set the run to 0, i.e. we reset it, and we look at how many times it's been triggered. Now if it's been triggered less than 20 times, then the threshold needs decreasing because it's quieter. The sound input coming in is quieter than we expected. If the trigger is greater than 155, and once again these two figures are what I've come across in trial and error, then the threshold is increased by 1, and you'll notice that it will drop faster than it will increase, and this is quite deliberate. If you don't do that, then what actually happens is it takes forever to establish a level if what you've got is a quiet passage in the music. And remember, I want these LEDs to be active all the time, doing something all the time, and they'll do something even if it's switched off, because gradually the trigger will get turned down and down and down until it starts triggering just with very low ambient noise. And here's request off. We look at the timer for the off signal, and if it's been on for off for a certain amount of time, then we turn on for a certain amount of time, then we turn the LEDs, all of the LEDs, off. State is 0, i.e. we've turned it off. Timer for off is 0. We reset that timer. And here we've got the sequence. Now all I'm doing here is I'm turning off all the pins, the RGB pins, and I'm getting a random number between 1 and 8, which means that in between 1 LED and 3 LEDs will be turned on. If you know your binary, you will know that 8 is, well, the random function on the Arduino would never return 8. It returns 7 as its maximum, because that max here is +1. So it will return in fact between 1 and 7. And if you know your binary, you know that 7 is 111, all LEDs on. So then we analyse our sequence number that we've just got, and if it's greater than 3, then it must be 4, so we write the blue LED to be high. We subtract 4 from the sequence, i.e. we cancel out that bit. And if the sequence is now greater than 1, we know it's got to be 2, so the green LED is going to be high, and we subtract another 2 from that sequence. And if the sequence is greater than 0, then we digital write the red LED high, because there's a 1 in there. So if there's 0, none of the LEDs will be high, none of the LEDs will be on. If it's a 1, the red LED will be on. If it's a 2 or a 3, then the green LED will be on. If it's a 4, a 5, a 6 or a 7, then the blue LED will be on. And this is how I've sequenced these LEDs. It's just a random sequence, but it's very, very effective, as you will see in the next video. So that's got all the technical bullshit out of the way, and we'll go on to the next video. Thank you very much.